Hi guys, and welcome to Astronomy 120. Last time there was a question by one of you guys about the lab of last time. And I was kind of, honestly, I confused the two labs between this lab and section 1. Your lab actually was supposed to be on 2 different days. And last time we rushed through the data, we didn't collect enough data, because after the lab, I realized that we really had to finish it today. So a lot of you last time did not have data even for 1 moon of Jupiter, let alone the other 3 moons. So the good news is it was planned all along. If you look at the syllabus, that this lab was supposed to be done on 2 different sessions. One last Thursday and another one today, because the time allotted for this lab for your section is kind of short. So there was no way we could have done all 4 moons of Jupiter on 1 day. So today we're going to continue the lab from last time and complete the entire lab basically and get all of the data. Does this make sense to you? The ones who are sitting in the lab, and I know quite a few of you are actually in this lab from this class are in the lab section. Those who are not sitting in Astronomy 125, ignore this part. Make sense? Okay, very good. So today we're continuing actually with section 2 of also the this week. This is the second session. So we're still continuing with light. Up to today, it's included in the exam, and the exam is planned this coming Thursday, a week from today, basically. So you still have plenty of review time to finish your review so that you can come to the exam ready for it. So this is in terms of stuff that is related to the class and the class flow and things like that. Make sense so far for everybody? So let me share the screen with you on unit 23 and 24. So again, last time when we talked about light, basically we gave all kinds of properties of light, namely light is a wave, and waves have wavelength, and light does have a wavelength. Light is also a wave, and also waves have frequency, and light also has a frequency. Waves have speed, and light also have a wave speed. As a matter of fact, the speed of light, which is the fastest anything can move with, and namely it has to be a massless object like light. So up to this point, it's light. Light is also carries with it energy, and because all waves carry with them energy. What is vibrating? Because when we have waves, we are talking about something going back and forth. And for this case, there are 2 things going back and forth. Electric field going back and forth, and the magnetic field is going back and forth. And I'm saying back and forth, although indicating up and down, because this orientation can be anywhere in space, okay? As long as the 2 are perpendicular to one another. If the electric field is going this way, the magnetic field is going up and down. So that's basically what it is. They have to remain perpendicular at all times and moving in a direction that is perpendicular to both of them. So these are the properties of light being a wave, and there is no mystery to that. So light is a wave. Experiments of Mr. Young, what Mr. Young in the early 1800s, what he did, he took a beam of light from one side and he ran it through 2 kind of openings called slits. So you have now 2 beams of light coming from 2 slits. And the reason why you wanted this one, you want the lights to be synchronized. You don't want it to be coming from 2 sources what is out of sync. So now it's only 1 light going through a dark screen, and that dark screen has 2 tiny openings called slits, and then it propagates after that from those 2 slits. And because light is a wave, basically the pattern that forms on it is similar to the pattern that forms on the surface of a lake. If you throw 2 rocks, you throw a rock, there will be circular formations around it. You throw another rock, there will be another circulations, and where they meet, they interfere. There will be places in there where there will be high intensity and places of low intensity. And that's exactly what Mr. Young saw, that there are fringes of dark light followed by, or bright light, followed by dark light, and so on and so forth. the superposition of the pattern indicating that light is indeed a wave, no question about it. He did also other experiments with a single slit, basically having light going through a very tiny opening, and the opening has to be very, very small one, slightly bigger than the wavelength of light, which is extremely small number. And patterns form also as they emerge. The diffusion patterns also have this similar behavior. So that is also 100% no doubter that light is a wave. Mr. Einstein actually took another experiments that people were doing and using the photoelectric effect and proved that light beyond the shadow of the doubt is actually a particle. He called it photons. Obviously, this is kind of contradictory. You can't be a wave, which is something that moves up and down, not really a particle at all, in a sense that it is carrying just energy. The medium does not really move from place to place, moves up and down, vibrates in a place. Waves have different distinctions. If I take a wave and combine it with another wave, I will have a new wave. That is a combination of the two. But if I have a particle and another particle and bring them next to one another, I still have one particle and another particle. Particles do not interfere. Particles, basically, they just combine. So this mystery, if you wish, turns out to be the nature of light. Light is actually dual nature. It's either it's in the same particle and in the same time also a wave. This duality, this two nature of light is actually brings itself to even particles. Electrons also have similar behavior. Electrons, which are supposed to be particles, sometimes they behave like waves. Hence, the electronic microscope that is used in science and actually in medical field too. Those they use the wave properties of electrons. Not only electrons, they do that, all particles do that. Which means that this duality really is not unique to light, exists everywhere. Even you and I have a wavelength in the sense that we are waves, although our waves are so focalized on one point that it doesn't make sense to talk about them. So we are, for the most part, particles or particle-like material. So this is basically the step from before. Now we're going to take it a step further. In the late 1800s, there was an interest in studying, if you take a spoon, for example, metallic spoon, not a plastic spoon, okay? Made out of iron, for example, and you put it on the stove. If you're going to do this experiment, you better be well protected. You need to have heat-resistant gloves. Don't wear the ones, the plastic ones, okay? Gloves that resist heat. Otherwise, the spoon is going to be very, very hot. So if you put the spoon on the stove, for example, or actually the iron that is on the stove, that is basically that matters. If you wait for a long time, a little bit long time, first of all, the spoon starts to heat up, and then it starts to change color. It becomes kind of dark red, and then red, brighter red, then it shifts toward orange, and then it becomes more and more, it could become potentially white. Provided it doesn't melt, provided it didn't reach the melting point of iron. So at that point, the material is emitting radiation. So the problem was of interest to a lot of scientists at that time, trying to understand what kind of light is produced, because it's making light. The spoon now is emitting light as it gets hotter and hotter and hotter. That problem became a famous problem, and people tried to understand it. Before doing that, they modeled it. They said, okay, a good emitter of light must be also a good observer of light. So they came up with an ideal body called the black body. This is an ideal body that can absorb everything you throw at it. So it appears black. Is it a real body? No, it's a theoretical body. It's a hypothetical body, because no matter what object you have, if you throw in all kinds of radiation to it, it will never absorb all of the material, all of the light. It will probably reflect some. So in this sense, the ideal body, the black body radiation is an ideal body. It's not realistic. It's not a practical one. But it's a model. That's basically what we do always in science. We make up something ideal, we study it. Once we understand it, then we go to the real stuff and try to see how it applies in real life. So that's exactly what happened in this situation. So the study of the black body radiation helped us understand a lot of things. In a sense, the sun is a black body because it's emitting radiation in all spectra. Because it's, like I said, a good observer also is a good emitter. So in this case, we're treating the sun as a black body. It doesn't mean that it's black. It means that it's emitting radiation in all frequencies as its internal engine is. The spoon that I was describing earlier, that is actually a black body. So you and I are actually a black body in this case, that we're emitting radiation. We're sitting right now in a room that is at room temperature. So if somebody were to detect the radiation that we're emitting, we're going to follow also the laws of the black body radiation. So this is basically the point I'm trying to say in here. Mr. actually Planck was the first person to really give us good explanation of the black body radiation. There were attempts before it. There was Mr. Not Kirchhoff, what's his name? I forgot his name right now, but he came up with an explanation, but that explanation broke down big time for short wavelength. So, and it was called the UV catastrophe. Okay. So the point being in here is this is a system that we're studying heavily in there, and that led to two laws that are of interest to us today, namely Stefan-Boltzmann law, which we will need, and also Wien's law. Okay, what are they? This in a nutshell. And I know for those sitting in Astronomy 125, we already have seen this laws actually practically. So Wien's law basically says the following. If I know the wavelength, I can find, if I know the maximum of the wavelength, I can find the temperature. There is a constant in here. Forget about the constant for a moment. Basically, if I know the wavelength, the maximum wavelength that it emitted. What I mean by that is, I take a spoon, for example, of the sun or myself or any object that I'm trying to study, and run it through a spectrometer. Find all of the different frequencies it emits, all the different wavelengths it produces. See which one is the maximum. Each one has the brightest, the more intense light is coming from it. Obviously, a green flower will emit, for the most part, the green light. The sun, for the most part, emits in the mid-range, which is really around the, we see it as white because it has all combinations, but it's actually around the green color, okay? You see whatever, so that if you start, for example, for the sun, and you measure the intensity of the red light, you will find it some. If you measure the intensity of the yellow light, you'll find it some. If you move to the green one, you will find it some, and the blue one, you will find it some. And there is a wide range in between all of these values. You will notice that it maxes at the green. And you do the same thing for all of them, for all of the objects you're trying to understand. Once you find the maximum wavelength, that's it. You know the temperature. You just use this mathematical expression. Now you know the temperature of that object. That's a very nice law. And then Stefan-Boltzmann law tells you how much radiation is emitted, how much energy is emitted per unit time from that system. Okay, if you know the temperature. So if you know the temperature, you take it to the power 4. And again, you multiply by constant. Ignore the constant for the moment. That is going to be the power emitted per unit area per unit time. Obviously, if you have a bigger area, you're going to emit more. If you wait a century, you're going to collect more energy. So that's the point in here. But for a second, for a square meter, this is how much energy you're getting. That's a very powerful stuff, because you have now, just by measuring one thing and one thing only, namely the maximum wavelength where it is. Once you find it, you find the temperature. Once you find the temperature, you know how much power that object is emitting per time, per second. I mean, per second, per area. That's what I meant to say. Okay. So this is in a nutshell what this unit is. So this is a black body. The sun is, okay? A body that absorbs all energy incident on it and emits all energy of all wavelengths is called a black body. That's by definition, because that's in terms of mathematical studies, in terms of modeling, and even experimental studies, that's easy to do. The sun, stovetop element, a piece of charcoal are all approximately a black body because they are not really emitting in all ranges. They are not absorbing in all frequencies, okay? That's really, in a nutshell, what that is. Even the sun is actually not an ideal one. So again, the studies have found the following. As all of them have this characteristic. So if I want to study how much is emitted per that black body, it depends on what its temperature is. Looking at the temperature of 6,000 Kelvin, I have the blue curve. At 5,000 Kelvin, which is about 1,000 Kelvin less, I'm emitting in the yellow line. At 4,000 Kelvin, the color, first of all, is kind of reddish overall, and I'm emitting in the red line. Okay. The peak frequency or the peak wavelength has shifted from left to slightly right to more right as the temperature went lower and lower. So as the temperature went lower, the wavelength increased. Okay. The wavelength increased with a decrease in temperature. See here, this expression? This is an inverse law. If the frequency goes, if the wavelength go down, the temperature go up. If the wavelength go up, higher and higher, then the temperature go down. And that's exactly what this curve is. The wavelength is going up. We're going from around 500 nanometer all the way to about actually more, but probably 800 nanometer, okay? Maybe 700 nanometer. This is actually 1,000 nanometer. So we're increasing in wavelength. As we're increasing in wavelength, the temperature is going down from 6,000 to around 4,000 Kelvin. Actually, it's a number in here is given to you. 725 for this light, 580 for the yellow, and 483 for the bluish color. Okay, so that is basically the different how this law is. So this is observed with experiment. Okay, and later on was divided into a law and actually a theoretical law also. So again, these are different. These are electrical burners in here, and as the temperature increases, please don't confuse the two. If you go at home and you try this experiment at home, just look at the burner only. If you have an electrical burner, if you turn on and you fix the power, at that point it's going to rise. The temperature reaches a certain point. It's not going to change after that because there is a coil, there is a resistor inside, and that resistor depends on how much current is running through it. It's going to produce a given power that is going to come off of it, electrical power that is going to come off of it. So the temperature, the color is not going to change anymore, even if you let it for 3 days on, okay? Because it's not going to get, obviously, because there is a dissipation of heat outside too, okay? There's no buildup of heat in that region. But the idea is the same. Which one is hotter? You guys know of these two in the picture? The yellow or the red? Those are your two choices. Come on, guys, there are only two choices. Which of these two is hotter? Which one has a higher temperature? The one on the left or the one on the right? The yellow color or the one on the red color? You guys hear me? I know you do, because one of you earlier commented. There is nothing wrong. Okay. Okay, thank you, Chiara. Anybody else? Which one is hotter? Okay. Yes, I think you're right. Okay, very good. Thank you, Ricardo. Yes, it's the yellow one, because again, the higher temperature always has this it's the one that if we go back in here, the yellow is hotter. The yellow is running about 5,000 Kelvin, whereas the red is about 4,000 Kelvin. Okay, it's very hot still. Again, the hotter body is the more slightly, so that it emits a shorter wavelength. So this is why the yellow is actually hotter in this scenario here. So this is Stefan-Boltzmann law. And again, the temperature is measured actually always use Kelvin. So please make sure note of that. So when you're doing exams, when you're doing labs, when you're doing some things like that, we measure unit in Kelvin, and Kelvin is one of the distinctions is doesn't have this degree next to it. Unlike the degree Celsius, which has a appended that 0 next to it, and degree Fahrenheit, which appended that 0 to it. One of the distinctions here is the Kelvin scale, which is a different way of measuring temperature, that's all. Is always positive, can never be negative. You cannot have an object that has a negative Kelvin temperature, number one. Number two, as a matter of fact, you cannot even have 0 Kelvin. 0 Kelvin is an ideal temperature, okay? It doesn't exist in real life, no matter how basically far advanced in the age of the universe, it's never going to reach 0 Kelvin exactly, okay? You have to have absolutely nothing in the universe to reach 0 Kelvin. 0 Kelvin will correspond to negative 273 degrees Celsius or negative 460 degrees Fahrenheit. And there is no upper limit to the temperature, okay? The sun is about 15 million Kelvin in its core, which is about 15 million degrees Celsius or 27 million degrees Fahrenheit. That's its core. And there are even hotter and hotter temperatures in the universe. Other stars have extremely higher temperatures than the sun does. And then that's not the hottest temperatures either. I mean, when the universe formed, it has even hotter and higher temperatures. So this is basically how the temperature is measured. We use the Kelvin scale. There is an interesting story for why that is, okay? And I don't think that we can run into it right now, but that's the point in here, okay? Again, this is the constant that you have. If you guys remember the lab we did, for those sitting in the lab, we had some lambdas and we were trying to find the temperatures and vice versa. And we found the maximum wavelength for the sun versus its temperature. As a matter of fact, you can throw in here 300 Kelvin, 300 Kelvin for yourself, because it works also the opposite too. 2.9 times 10 to the power 6 in the numerator, Kelvin per nanometer. Cancel the Kelvin with the Kelvin, and you're gonna find what's your maximum wavelength you're gonna be emitting at. Of course, it's gonna be in the infrared. That's the region. It's gonna be below the red, because we use goggles to see living organisms. 300 Kelvin is your average temperature, okay, on a daily basis. It may be 310 on a hot day. It may be 293 on a cold day, but that's about 300 Kelvin. Okay, so this is basically, it's a useful law, as I was saying. Knowing the maximum wavelength, we can find the temperature. Now, if I measure the area underneath, basically this curve, it will tell you how much energy was emitted, okay? The area underneath per wavelength, basically the sum all of the wavelength, all of them. Add up all of the contributions, not just one single frequency, add them all. That's what the area is really. It's summing all of these values under the curve. In calculus, for those who took calculus or planning on taking calculus or dealing with calculus, this is actually an integration and coordinate integral. Obviously, there will be more power for a higher temperature than a lower temperature. 4,000 Kelvin would barely produce much energy versus a 6,000 Kelvin. But how big it is? I mean, if you take the burner and you just barely turn it on, you're going to produce some heat. But if you turn it all the way on, you're going to produce more heat per unit time. So more energy is going to be produced, basically, for the same amount of time. Obviously, if you barely turn on the heat, you're going to produce a lot of heat if you waited for a long time, versus if you turn on and off the higher temperature. So it's not going to produce, it's going to produce more heat during that moment. So time matters, okay? So this is Stefan-Boltzmann law, okay? Where this constant is a tiny constant, it's about 5.67. It's easy to remember. It's 567 times 10 to the negative 8, 5678. And so basically, this gives you now the amount of energy that is emitted per unit area, square meters, and also per unit time, which is watts, okay? So for the case of the sun, it produces a lot. Basically, the temperature of the sun is 5,800 Kelvin. So we're going to plug in 5,800 in here, and you multiply 5,800 by 5,800, get you some huge number, about what, about 30,000 or something? No, 30,000, 30 million. And then you're going to multiply that 30. So it's going to be a huge number. At the end of the day, 64 million watts per square meter, okay? I may have to do it personally. If 5,000, that's what, 25 million. Yeah, but don't forget you have 10 to the negative 8 in here. That's going to drop, shut it down. Okay. Yeah, so that's basically in a nutshell what that number is. 64 million joules per second per square meter. Remember, the sun has a 700,000 kilometers of radius. So you take that and you multiply it by, you square that number and you multiply it by 4 pi. And now that is the entire area of the sun. And you will see how much ridiculous amount of energy is produced by the sun every second. And that part of it will come in here to the earth. The other part spread everywhere around the sun and goes everywhere. And that tiny part that comes in here from that huge number is what is causing the entire planet to exist, actually. I mean, life to evolve on its surface. So the surface temperature of the sun is 5,800 Kelvin, 5,800 Kelvin. That's why it appears in this color. It has some spots in here, which are part of a discussion for another unit. And it radiates in all of the different areas about 64 million kilometers per square meter per second. So this is basically how much energy per square meter per second is produced. So this is this unit. So again, the moral of the story today is if you know the maximum wavelength, you should be able to find where what the temperature is. Once you find what the temperature is, you could tell what the power that is produced per unit time the power is per unit time, so it's the energy per unit time per unit area. Let me share with you the last unit from this week, which is unit 24, and that actually delves also in some of the stuff that we did actually in the lab too. It talks about the spectrum of the different materials in here, spectra, and how can we have an emission spectrum and or an absorption spectrum, and what does that mean? So every element now, the reason why you have light, again, being absorbed by a material to begin with, is because it goes into the internal structure of the material and basically excite it. If it's a low energy wavelength, long wavelength, it's going to impact its molecules, for example, and make them vibrate one way or the other. But if it's a shorter wavelength, it could go and impact the atom itself and cause it to get excited and then have its electron jump from one energy level to an energy level. These are higher energy that they are going to be not affecting the molecules, because the molecules are of a large scale compared to the atoms. And even if it's higher energy, meaning the frequency is so high, the light can go and penetrate all the way into the nucleus and start messing around with the protons and the neutrons themselves. So depending on the wavelength, this is basically how the materials are affected by it. Some wavelengths are extremely long that they are probably, they need mountains to interact with, or planets to interact with on that scale. So again, light is made up of different spectra, different frequencies, and this is basically of a spectrum of a given element in here, given material. Obviously, I'm shining a light on it in here from a source, and this is giving me a spectrum that is dipping at certain frequencies in here. So obviously, this is an absorption spectrum, because I'm letting everything run through except some of them. If I bring another material, I will find this peaks, or in this case, drops. They will not be in the same point, because spectrum is unique. Spectral lines are unique to a given element, whether absorption or emission. Okay. And this was a puzzle before Mr. Bohr. People were really puzzled exactly what's going on in here. Why do we have this distinct lines that seem to be unique to different elements? Unique signatures. So the understanding at that time, especially for the visible light is kind of long wavelengths to fall into this picture. Okay, energy enough to go into the atoms themselves. So the visible light was an issue. So people thought, okay, how can we interpret it in terms of the atom? So the belief was the atom was, and actually the understanding based on experiments, the atom has negative charges in it. There is no question about it. You can detect the negative charges in it, called electrons at that time. So people built a model and said, okay, let's have the atom made up of this negative charges. Obviously, atom is not negatively charged, and otherwise all light should be flying. I mean, electrical signals should be flying every which way. Lightning should be everywhere, but it's not. Most of the materials are neutral. All of the materials are neutral, for that matter of fact, except under some extreme conditions when they are not neutral. So in this situation, light must be neutral. So to counterbalance these charges, we must have a positive charges everywhere in here. So that was the understanding. Obviously, this did not fit another experiment that Mr. Rutherford has run, where he saw that the atoms, for the most part, are empty space. So this picture is wrong. So now the picture then that emerged, that I have a positive charge in the center, and I have negative charges outside of that circle. That's how the atom appears to be. Then Mr. Bohr, before him, they were suggesting that if this is true, because this is a negative charge and this is a positive charge, atoms should not exist at all, because the electron will spiral down and fall into the atom, into the nucleus, I'm sorry. And it will fall before you even blink your eye. So atoms should not really exist if this is true, and use classical mechanics to interpret it. That's where Mr. Bohr came up with a model, and that model somehow explained those spectra. He suggested that there is a quantity called angular momentum of the electron as it spins around the positively charged one, and this angular momentum must be in resonance so that it will never cancel, meaning it has its wavelength must be an integer multiple of the path that it is going around the sun. So in this case, I wrote about 3 times, probably 4 times. As long as you have a given number, 1, 2, 3, 4, so it will always stay in orbit. So because of that, yeah, now he was able to explain this different transitions and this different spectra, that in order for an atom, for a frequency to be emitted or absorbed, the light has to be exactly the energy corresponding to the difference in these 2 different levels. And that frequency is given by a constant h, would happen to be the same constant that Mr. Planck was working with, times the frequency of the light that is either being emitted or absorbed. So the difference between 2 different energy levels, if I am going up, I'm absorbing energy. So this is part of an absorption spectrum. Then going down from an excited state to the ground state. Then in this scenario, I am actually emitting light. So light is going to come off of this, be produced. Light is absorbed in the first case by the atom to go from a ground state to a higher state. So that's basically, I drew a picture between, let's say, ground state and the second energy level. It could be between the ground and the first, or between the ground and the third, or between actually the first and the third, or the first and the second, and both were up and down. So this is in a nutshell how emission based on the Niels Bohr model for the hydrogen atom. His model did not work for any other metal and any other material. So we needed really something else called quantum mechanics to explain everything else. But this is basically in a nutshell what you have. Transition of this high between this level and this level is kind of short transition. Does not require much energy. And remember, the energy and the wavelength are, the energy is related to the frequency, and the frequency is inversely related to the wavelength. So this is h times frequency, where h is just a constant. It's just a number that is 6.626 times 10 to the negative 34. It's just a constant, okay? For right now, it doesn't matter what its value is. So h is a constant. C is speed of light divided by a wavelength. That is actually the frequency. So the bottom line is, because the energy is less, the wavelength is actually long, and the color is red. The frequency is less too, because remember, E is equal to HF. So if there is less energy, that means less frequency. But because the wavelength is inversely proportional to, because it's speed of light divided by the frequency. So if we're dealing with less frequency, the wavelength is long. So that's basically in a nutshell what that is. Now, a transition from this far away all the way to here will result to a shorter wavelength, higher frequency. Okay. So in both cases, these are emission spectra. In which case, I'm going to get either a red color or a blue color. Blue color is higher frequency, which means shorter wavelength, and it's coming from a higher energy level down to a lower energy level, far greater than from this higher energy level to this lower energy level. Okay, and these are the different spectra that can be formed, at least up to level 2. These are the so-called Lyman spectra. So in this case, is you have energy. The end energy is the end state is 2. So that's where you're going to end up with. Okay, this is for hydrogen. Either you come from 3 to 2 and you produce this red light, which is about 656 nanometers. Or you come from 4 to 5, from 4 to 2, I'm sorry. From 4 to 2, you produce this color, okay, which is kind of blue color. And there is another one, which is a low intensity. When we do the spectra, it's very hard to see. And actually, these two are very close from one another, from 5 to 2. And as you move along, there is another one in here, and these are really the visible lights that you're going to produce, about 4 of them. The others are very close from each other, about 400 nanometers. And that's the end of it in the visible range for hydrogen. There are in the infrared on this side, and there is the ultraviolet on this side, but we can't see them with our naked eyes. So remember, all of these experiments were done in the time before we had better ways of understanding even the longer wavelengths or a shorter wavelength. Another atom will produce a different spectrum. Another atom will have a different spectrum in this case, okay? The red might be here, the yellow might be here, and so on and so forth, and the lines will be completely different, okay, than the case of hydrogen. So every single atom will have its unique signature and with its unique values in it. So it's not just a pattern, it's not just the pattern, but also the values. This red from this atom is not the same red from the other one, from the hydrogen atom. So each element has a different line on the spectral line. So different versions of red are different values, actually. It's not just the pattern, it's actually numerical values. So the absorption spectrum is that when you have a hot source behind behind the source in here, and that runs to through a material, then in this case, all of the light coming from the hot source to you will come back in here, except with some missing lines in it. Missing because they were absorbed by this element in here. If you take this line in here and you project them into the emission spectrum of hydrogen, so emission for hydrogen, in this case, hydrogen itself is excited and the surrounding about it is not that hot. So that you have, in this case, an emission. And you will have this lines. This line will be missing in the emission spectrum for hydrogen. Sorry, where is in this experiment, okay? It will be the same line in here. So emission spectrum and absorption spectrum are opposite to one another, whether light is being emitted by the material when the surrounding is cold, or when it's absorbed by the material where there is a hot source behind it, and then all of the light is coming through, with the exception of the ones that have been absorbed by the material. So this is in a nutshell what Kirchhoff's laws in here for the emission of light are. So you have three types of spectrum. This is a continuous spectrum, everything is in there. In this case, nothing in there except some elements in here. This is obviously an emission spectrum. An absorption spectrum is that all of the light is coming through with the exception of some missing ones. This line in here, they will correspond in values to the exact same lines for the absorption for the same material. Okay. Now, if you look at this single material, you will find different, basically, signatures from different elements. I have in here frequency that corresponds to hydrogen. I have another frequency corresponding to hydrogen, and may have more hydrogen lines in here. Therefore, I conclude hydrogen exists in this material. Obviously, this is an absorption spectrum because I'm getting all light except some that are missing. And I could have also the signature of sodium because I have this frequency that is unique to sodium. And if I have another one, that would be unique to sodium and so on. So magnesium in this case, calcium. So every time I find those exact values with that pattern, then I know for sure I have those elements that exist in that cloud or that star or whatever object is. This is really how stuff is. This is extremely fascinating things. And when we run this by the sun, this is basically how much composition is. The sun is mainly hydrogen, 70% hydrogen, 27% helium, and the rest are traces of all of the other carbons. Because light is coming from the sun in all of the different frequencies, and it's being absorbed by the atmosphere of the sun. Or I'm sorry, the light is being absorbed by the atmosphere of the sun. So this is what we went through, and this is the composition. So it's really a powerful technique up to this point. You can look at the frequency, find the lambda max. Once you know the lambda max, you can find the temperature of that object. You can find how much power is generated by that star, how much bright it should be, intrinsic proper brightness. And if you measure the actual brightness and how you see it versus the actual one, then you can tell how far the object is. It's really, because if you take a candle next to you and you see it, now it has so much luminosity, but if you push it very far away, obviously it dims. So the further away it dims, then now you can find how far the star is. Then you study the spectral lines also from the same star and see what is missing. In this case, you will find its composition. And if you know its composition, you know it's really its history, because 75% of the hydrogen 75% of the star will need to be hydrogen, 25% of the star need to be helium. If it deviates any from these numbers, that means it is not the original generation of stars, but that forms when the universe formed. So everything fits in this case. We have actually developed enough understanding to move forward. We still have another topic to discover. Then we're going to move to the units of the 50s. So next week, we will have the Tuesday session, but there will be no Thursday session because we will have our exam. So we'll try to get some of the materials in, but the stuff that is next week is not part of this exam. Good. Are we good, guys? Make sense? Okay, very good. Thank you, guys. I'll see you, those who are sitting in the Astronomy 125 a little later today. The others, I'll see you guys on Tuesday of next week. Thank you.